So no news yet. So I'm in thumb. Not with this, but you're right. I could get a phone call anytime. So I got my phone right here, fully charged and ready to go in my pocket, and just waiting to hear. What's that? Not in here, but it was sitting fully charged before I brought it in here. So, okay, let's talk about the plan moving forward. So my plan is what we're going to do today is structural analysis, and then our next lecture, which honestly is probably going to be online, is going to be structural design. Now, here's what I'm going to do on the lecture is I'm going to talk about steel and concrete. But when it comes to your quiz, I'm probably just going to do concrete because I'm well aware that everybody is probably going to take the steel questions and go C or A or 10 out of 10 guarantee or what have you. So I'm, that's fine. And plus, if you want, there's this really, really horrible teacher teaching it next semester, so you can take it and learn all about it. Next semester, that's the plan.
I'll do all 3 classes. All 3. All semester.
Hey, for those of you that are in co-op, we have some pretty funny discussions in there, don't we? We had a pretty good one yesterday talking about ethics. It was pretty good. Although we had a pretty good one in here the other day too. All right, okay.
That was a great class.
Okay, all right, settle down. So the quiz, pay attention. All right, so the quiz for statics, dynamics, ethics, that closed. The solution should be active online, so you all can review that. What I'm going to do for quiz 5, again, I'm going to combine structural analysis and structural design into one quiz because it's all kind of the same topic, or not the same topic, but it all sort of flows together. It's probably going to be like 8 to 10 questions, but if I'm not putting steel on there, it actually might be fewer. So, and those questions are, they do tend to be a little bit bigger and a little bit longer, so you'll get a little more time on those accordingly. So today, what I'm going to do is I'm going to talk about structural analysis, okay? So just so you're aware, okay, oops, sorry, mouse got a little nuts. Okay, so really what we're talking about is, and what we're going to try and cover in here is forces in structures. So that's, reactions, that's truss analysis, that's shear diagrams, moment diagrams. I'm actually not going to directly have some examples on reactions because a couple reasons. One, we've already done statics. We're going to have a mechanics and materials section later, and so I want to focus on the stuff that I think is purely related to structures. So I do want to talk about trusses and shear and moment and things like that. We are going to have problems on deflections, okay? And so my advice when it comes to deflections, I'll just go ahead and say it right now, is there's really 2 main methods that you need to be able to utilize on the exam. And that's the principle of virtual work, that the unit load method where you put the single 1 kip load or what have you. Or when it comes to beams, bless you, a really good potential option is to just use the formulas that are in the manual. We're going to have an example looking right at that. Okay, oh, I need to get the sign sheet passed around. Now, LRFD load combinations actually sort of fall within structural analysis. So if you all remember the tributary area stuff that we talked about in concrete design, that's technically a structural analysis concept. So I'm going to talk about that today. I have here influence lines if we have time. I don't have an example prepared on influence lines, but honestly what we talk about today is probably going to take up a fair amount of time. So I don't think we're going to get to it just based on concepts of time. Excuse me. So here's sort of the general patterns of what we're talking about. So analysis of forces, deflections, determinacy, et cetera, 6 to 9 questions. This chair right here, I'm moving this. I keep walking into it. I'm like, why is it over here? Where? I'm going to have to. Why are there so many chairs in this room? It's crazy. All right. So I'm just going to get right into it. So just so you're aware, we've got 1, 2, 3, 4, 5 examples, and these examples are they're gonna take some time, okay? So there are some pretty involved examples, okay? So we're gonna start with the first one, work our way down. Okay, now, for the plane truss shown below, what is most nearly the axial force in member CG? And we've got some compression, tension, etc. Now, let's talk about strategy, okay? Who thinks that the method of joints on this problem is a good idea? Who remembers what the method of joints is?
I know there's a lot of them that we shouldn't use.
There we go. Let's go with sections, is that what you said? You're exactly right, okay? The purpose of this problem is to get you thinking about structural analysis again, but it's also to make a good point. This problem is a very classical problem on the FE exam where you're given a truss and they ask for the force in a given member. It's a very classical problem on the FE. And dependent upon the truss, you could use method of joints or method of sections, but more often than not, the truss tends to be really big, and it's, you know, in this case, you'd have to solve a lot of joints to get to member CG, so in this instance, method of section seems to make the most sense. Now, when I cut a section, answer me this, would I look to the left or look to the right? Now, why are you saying, I hear a couple people saying right. Somebody tell me why.
Because of your reaction.
Because of the reactions, exactly right. If I cut a section and I look to the right, I don't have to deal with the support reactions at point A and point F. So I don't have to solve for them. All I have to do is cut a section, look to the right, and that's it. There's nothing else that needs to be done. So again, secret weapon of structural engineering, I'm going to cut a section, and I'm going to cut a vertical section between B and C and look to the right. So we'll draw that out, and let's see what it looks like. Okay. Wait, hold on. Well, it's blinking. There, okay, never mind. I moved the little box, and it sort of like beeped at me, and I went, uh-oh. All right, so example 1. So we're going to cut a section and look to the right, and so here's what we've got. All right, so let's see, we have, the truss looks like this. It goes down, and it comes up like that. All right, and then we have a vertical member that comes down like this. We have that. We have another vertical member that comes down like this, like that. And then we have this. And basically, this is what our structure looks like. Okay. Now, for sake of discussion, one thing I'm going to do, we'll do that, that, and that, just to sort of show what's going on past the structure. Okay. Now let's start naming some points. This is C, this is D, this is E, this is J, this is I. Oh, hold on. Let me do something. Let me put the E right here because there's diagonal members. Diagonal member right there. So this is I, this is H, and then this point right here, that's G, and that point is B. Okay. Now in terms of loads, I have 40 kips right here. I have 40 kips right here, and I have 20 kips right here. Okay. Now, let's see. All right, let's put some dimensions on here. Now, this is not drawn very well in terms of scale, so forgive me for that, but you all should have straight edges. So this is 20 feet, 20 feet, 20 feet, and then that's sort of what our structure looks like. And then somebody help me out. What is this dimension right here? Does anybody have this one? 10. This is 10. And then at the very, very end of the truss, it's 30, right? So that would mean this one is 25, right? So the idea is that, like, remember BG is 25 foot long, this one's 20, this one's 15, and that one's 10. Does that make sense? Okay, all right. Now, a couple things. Whenever you're utilizing the method of sections, when in doubt, always assume that your members are experiencing tension, okay? Because whenever you get a negative answer, remember, it does not mean you need to develop significant emotional distress. It just means that you assumed incorrectly and it's in compression. That's okay. All right, so here's what I'm going to do. I'm going to indicate this is in tension, and we'll call this GH, okay? We're going to indicate this is in tension, and this is CG, okay? All right. What I'm going to do for CG is I'm going to split it up into CGX, CGY, and then the same thing here. This is member BC, BCX, BCY. Okay? Now, I'm going to do the problem the way that I think is probably most natural for you in terms of how I think you would do the problem. There is a little bit more of a efficient way of doing it, and I'll show you that at the end. But let's just go back to fundamentals, okay? When you cut a section and you use the method of sections for truss analysis, you're doing that because you've got three equations of equilibrium at your disposal, okay? You've got sum of forces in the x direction, sum of forces in the y direction, and sum of moments, okay? When you're summing moments for using the method of sections, you always want to sum moments where two of the forces intersect. So you tell me, where do you think is a good place summing moments for this truss? G, okay? Usually what you want to do is that, for instance, if you're trying to solve for all of the forces along a diagonal, you at least, or along a given section cut, you at least want to try and eliminate at least one of the diagonals. So let's sum moments at G. So I'm going to sum moments at G. Here, let me move this up here a little bit. So let's sum moments at G. All right? Oh, come on. Sum moments at G. Okay. Let's see. I didn't leave any loads off, did I? Am I good there? Okay, all right. So summing moments at G. Let's deal with our external loads first. And the way I see it, I've got 40 times 20, 40 times 40, and 20 times 60. Did I do that right? All right, and they're all rotating in a clockwise fashion. So I've got 40 times 20. I've got 40 times 40. And I've got 20 times 60. Okay? Everybody okay with that? All right. Now, since I'm summing moments at G, do I have to deal with GH? No. Do I have to deal with CGX or CGY? No. I do have to deal with BC, okay? Now, if you remember that little fancy word in truss analysis, the principle of transmissibility, the idea that those forces act anywhere along that line of action, I can move BCX and BCY in that fashion anywhere along that line. What I'm going to do is I'm going to move them up here to B, okay? So imagine that BCX is right here and BCY is right there, okay? So in that instance, do I have to deal with the Y component? No, because it goes right through it. All I have to deal with is BCX which is generating moment this way, so that belongs on the right side of the table. So I've got BCX at a moment arm of what? 25, right? Because we're talking about the vertical, right? And remember, BG is 25 foot tall. Oh. Bless you. Gotta bring your laptop. All right, everybody okay with that? Okay, so somebody help me out over here on the left. What's 40 times 20, 40 times 40, and 20 times 60 give you? 3,600? And that's foot kips equals BCX times 25 feet. So BCX is what? Positive 144 kips. Do I have a second on that? And so that's 144 kips, and that is in fact going to the left. Okay? In other words, we assumed tension and we got a positive answer. So BC is a member that is experiencing tension. Now we know the X component of BC, but we don't know the Y component. Now how would we determine the Y component? The slope ratio, okay? So let's look at that slope ratio. You get out of my way. All right, so the slope ratio for BC. Okay, what is the slope ratio of BC? Can anybody tell me what that is? Say it again. 1 to 5. Well, hold on. I'm getting something different. Let me see. See, I'm getting 1 to 4 because if we're looking at this diagonal, okay, just pay attention to this diagonal. How far up do we go from here to here? We'll go up 20, right? Like just for the diagonal as a whole. We go up 20 and we go over 80. So 20 and 80, that's 1 and 4, right? So what I would say is that is 1 to 4. In other words, BCX is to 4 as BCY is to 1. Everybody okay with that? So BCY is 1/4 BCX, which is 1/4 of 144 kips, which is what? What is 1/4 of that? 36 kips. And which direction is that going to go? It's BCY, so it's up or down. It's got to go up because we assumed correctly for BC in general. Okay, sound good? Now, you tell me, if you were just solving this structure, what would you do next? We have to sum forces, but which direction? X direction or Y direction? Why? Because we've got 2 unknown horizontal components, but we have only 1 unknown vertical component, right? So we don't need to go through and solve the horizontal. I mean, we could, but we'd end up having to go back and plug anyways. So we could. That's a great point. So the question is, don't we need to find BC as a whole? Well, we could, but we don't really care for this problem. And that's something to keep in mind whenever you're working on the FE. Always keep your eye on the prize, okay? The question said, what's CG? Don't, once you find CG, stop. And I'm actually going to make a point about that here in a sec. So, you said some forces in the Y direction. So, here, forgive me, I'm probably going to go up and down a little bit. All right. So here's my structure. Let's start off with the external loads. I got 40, 40, and 20 all going down. So 40 kips, 40 kips, 20 kips, all going down. What else do I have going down? CGY. Okay? Do I have anything going up? Exactly. BCY is 36, yeah. BCY is 36 kips. Okay? And that's it, right? So 36 kips equals CGY plus 40, 40, and 20 is 100. So therefore, CGY is what? It's not 64. Negative 64, which is 64 kips going up, okay? And so what Mr. Fitzpatrick just said is that this is in compression, okay? What does that do for our problem? It eliminates two of the choices, exactly, because there's two in tension, two in compression. So there's two of our choices right there, okay? What else could we do right now? Look at this number, 64. What are the two choices? Let's go back to the problem. Right here, we could stop. Think about it. We know it's in compression, right? So that one's eliminated, that one's eliminated. But we got that the y component was what? 64? So is it A? If the y component is 64, well, the hypotenuse can't be 45. It's got to be that. So we could stop right now. Now I'm gonna continue this forward a little bit, just so that we're clear. All right. This member CG, okay? If you look at member CG, you go over 20. And how far do you go up? How tall is member CH? It's 20. So this member is at a 1-to-1 slope ratio. So if you're a mathematical purist, what you can say is this. Looking at the slope ratio, this member is at a 1-to-1 square root of 2. So CGY is to 1 as CG is to the square root of 2. Therefore, CG is CGY times the square root of 2. So what is 64 kips times the square root of 2? 90.5 kips. Finally, one of them C. All right. Before I move on, this should probably have shaken the rust off for some of you. Well, I know that there's a couple people in here that are taking me for structural analysis right now, and we just had a celebration today on this, so they're like, oh, God, I'm tired of this stuff. They're like, no comment, Dr. Mike. All right. Any question on this?
So if we wanted to not get to the separation that we could technically sum volume at H and then solve for the CGX, technically, right?
Well, here's the thing about summing moments at H. I'm glad you mentioned that. The thing about summing moments at H is, like, if that's how you start, well, you can eliminate GH. But if you move both of these diagonals up to C, you're going to have two components. Do you see what I mean? You're going to have two horizontal components. Now, if you really wanted to get specific, okay, all right, whenever you sum forces, whenever you sum moments, the goal is to eliminate two of the unknowns and only solve for the other, right? So if your goal is member CG, where do you sum moments to eliminate the other two? And the answer is like there. Because if you sum moments like right here, I'll put it on the video. Like if you sum moments, track that out, and it's like over here or something. Well, member BC and member GH intersect at that point, so you can solve for CG directly. The only thing is, I don't think that's as natural. I don't think that's what your natural instinct is, and it's going to require a little bit more geometry. And it's not difficult. You can figure it out. I just don't think that's naturally what you're going to do. But you would do the problem faster, that's for sure. And if you did that, you would get ultimately that CG is 90 point, whatever 2 kits, so, or 0.5 kits. Did that answer your question? That was a good question, though.
So that way you can take the CG down to G and eliminate X.
Exactly. Or take it all the way up there if you want. Take it, up to the 2nd floor. Yeah. So yeah, so you could do that, yes. Fair point. Any other questions? This is good stuff. All right. Next problem. Okay. For the beams shown below, what is most nearly the largest magnitude of bending moment due to the applied loads? So we got to break out the shear diagram, break out the moment diagram, okay? What? That's a great question, and I actually want. No, hold on. That's a. Let me say something about that. So the question was, what about the little formulas for shear and moment? First off, there is a very shortened version of that in the reference manual for basic beams. Okay, it's in the reference manual. It is certainly not as verbose as what I gave you in concrete design, not by a mile. And 2, the problem is that even if you had that wouldn't help you here because the loading is too complicated. And so really you just have to chug it out. Before we get into this problem, I want to say something. With this problem and this type of problem on the FE, typically what would happen is you would get one of two types of situations. Okay. The first is they might ask you something like this, like what's most nearly the largest magnitude of moment. The other thing they might ask you is they might say, what's the moment right here? Or what's the moment right here? Like they might just pick a point and say, what's the moment at C? Or what's the shear at C? Or what have you. That's a very common problem on the FE as well. And if you get a problem like that, don't draw the shear diagram or moment diagram. Don't do that at all. Just once you get your reactions, cut you a section at the point of interest, look either way, and just sum forces or sum moments. Don't go through all the trouble of drawing the shear diagram and the moment diagram because you're just wasting time. But if they ask you to figure out, M max or shear max, well, you got to go through it and chug it out. So, okay. All right. So for the beam shown below, what's most nearly the largest magnitude of bending moment? Okay. So first thing we got to do is we have to determine what? Support reactions. There we go. All right. Now, let me redraw this as I'm going to kind of need the structure. So it would help if I actually drew with a marker and not the eraser. I'm a little scatterbrained, as I'm sure you can imagine. I'm surprised I even made it through that first problem.
You're in distress.
I'm not in distress. I've just got a lot on my mind. At this moment. Hold on. I'm having a hard time even figuring out what I'm supposed to do right now. Because you all have to draw it too, and I figured be nice. Oh my goodness.
What's she doing?
she's probably doing a little more than that. Goodness gracious.
Is she walking around?
Probably breathing. Sure breathing.
I love this job. I really do. To you all.
I feel like sometimes you say a little just drop like things to yourself.
Language, sir.
I heard about breathing. I'm sorry.
I'm glad that the microphone is over here. Well, thank you for being considerate. All right. All right, everybody, settle down. All right, so this is 6 feet, this is 4 feet, this is 4 feet, this is 10 feet, this is 6 feet, and then we've got reactions. I'm going to go ahead and assume they both act upward, so this is AY, this is BY. There's another reason we didn't have a problem just on reactions, because we kind of have to do it anyways. 6 kips per foot. This is 20 kips. And this is 4 kips per foot. Okay? Now, so here's our structure. Now, remember, when we determine support reactions, we can idealize those distributed loads as a point load. But remember, when we draw shear and moment diagrams, those don't exist, okay? We just place those there to make our lives easier when determining support reactions. For example, that distributed load on the left, we have 6 kips per foot acting over a distance of 6 feet, right? So I can idealize that as a single concentrated load of what? 36 kips, okay? And from A, how far is that? 3 feet. But remember, that 36 kips doesn't exist when we draw the shear diagram and moment diagram, okay? This distributed load, the 4 kips per foot, I have 4 kips per foot acting over a distance of what? 16. And so 16 times 4 is 64, and that's going to be somewhere about right there. So 64 kips. And then that distance is what? Say it again. 8. All right. Sound good? All right. In order to determine our reactions, I propose we need to sum moments at one of these points to determine the reaction at the other point. What do you want me to do? You want me to sum moments at B? I sum moments today. So I'm going to... No. No, it doesn't. Well, that would matter. That's a good point. Technically, we are supposed to draw an AX, but since there's no horizontal loads, it's 0. All right. Okay. So help me out. I'm going to need your help. So we're summing moments at B. So do I need to deal with BY? Breathe, settle down, sir. Do I need to deal with BY? What about the 64 kips? Okay, which side of the table does it belong on, left or right? And what's the moment arm? 2 feet. So 64 kips, 2 feet. All right. What about the 20 kips? Do I need to account for that? All right. Left or right? And what's the moment arm? 14 feet. Okay, the 36 kips, that's also going to go on this side. And what's the moment arm? How far is it from B? So 10, 14, 18, 21, right? Am I missing anything? AY going in the opposite direction, and what's that moment arm? 18. So we have AY times 18 feet equals what? So 128 plus 280 plus something. Say it again. 1164. Do I have a second on that? All right, and then AY is what? What's 164 or 1164 over 18? And that's positive 64.67 kips. So that's 64.67 kips going upwards. Okay, so if you want, we'll say 64.67 kips going upward. All right. Then we sum forces in the y direction. Everything going up, everything going down. So we have 36 kips going down, 20 kips going down, 64 kips going down. And going upwards, we have AY. Yes?
Since the kind of A1, it's been a while since I've done this, I'm kind of thinking that we just do like the left half of the beam and not worry about, because like the right half is just 4 kips per foot over 6 feet, because that cantilever section, so we know that the left side would be more. I'm just saying instead of doing like summit to get BY, we just look at the shear moment left, like up until BY. Sorry, go ahead.
What?
I was just wondering if we had.
He's saying like the maximum is going to be on the far left side.
We don't know that. The reason why is because look, you're making a point that on a cantilevered section you can have a significant moment. And so let me say this. It's very possible that given the distribution of moment that you have an Mmax right here because you have a large cantilevered moment sticking out. But unless you can see into the future and see the distribution of shears and moments across the rest of the structure, you don't know. Like here's an easy way of explaining it. You might very well be correct if the loads are as they are. But what if this 20 kips was suddenly 80 kips? You might be wrong, okay? And really the only way to truly know is to go through and chug it out.
We can't find that max without BY, like this intersection.
Now I'm
We can't find the max moment on this intersection without BY. That's why we have to find it. I was just saying the 6-foot section on the right side, we know is not the max moment.
That's true. That's true.
Okay, so do we need BY to get the moment for this intersection, or can we just use AY? Still find the moment.
I guess you could. I guess that you're talking about only drawing the shear diagram and the moment diagram from here over. You could do that. You could. I think from an over, like if you're that comfortable with the process, you could do that. But you wouldn't give a more complete answer. Let me go back to your question once I finish, and I think I'll be able to respond to it a little more eloquently. So, all right. So this is 64.67 kips. Then there's BY. So we have BY plus 64.67 kips equals, okay, 36 plus 20. That's 56 plus 64. That's 120. And BY is then positive what? What is it? 55.33 kips, which is 55.33 kips going upward. All right. Does everybody have this? Everybody got this? All right. So the first thing to do is, now that we've got this, if we're trying to determine maximum moment, we need to draw the shear diagram, then draw the moment diagram. So let's go through that. you know. That's actually a pretty good question, and the answer is like yes, almost to an infinite extent. That you have these like pads that like you'll get a pad and it has something like 5 sheets of paper on it or something like that, and then you'll use that up, and when you're done, they'll give you another one. They just keep replenishing them. So they're like really big. I mean, I know that sounds weird.
It's like 11 by 17.
They're really big. Yeah. Now, okay, so we're going to start off with the shear diagram. Okay, remember, when you're drawing the shear diagram, you do what the beam tells you to do. Okay, so I start off at 0. So everybody follow with me up here, okay? So you start at 0, okay? And then you go down. You're going to start at 0, and you're ultimately going to get right here, and you're going to go down to minus 36. Now, how did I know that? Because from here to here, there's 6 kips per foot for a distance of 6 feet. 6 times 6 is 36. Now, how do I get down there? Well, the load is constant, so the slope is constant. And so if you have a constant slope, that is a straight line. All right? And remember, you do what the beam tells you to do. So I'm going down, going down, going down. And then it says, Greg, go up. So if I'm at negative 36 and I go up 64.67, what does that put me at? 28.67. All right? Then no change, no change, no change, no change. Greg, go down 20. Okay. So if I'm at 28.67 and I go down, what's that? It knows me pretty well. The beam and I are on a first name basis. No. I tried to think of a funny answer. I couldn't think of one. Just no. All right. So if I'm at 28.67, I go down 20. I'm at 8.67. Okay? Then I go over, go over, go over. Okay. Now, I start to see a little bit of load onsetting. Okay? Now, this is where that 64 kips gets really confusing. Remember, that 64 kips doesn't exist, okay? We made that up to determine reactions. It made our reaction computation easier. So from here to here, how far down do I go? Well, it's 4 kips per foot over a distance of 10 feet, so 40. And so if I'm at 8.67 and I go down 40, what does that put me at? There we go. So that's going to put me about right there, and that's going to be a straight line. So that's minus 31.33. And then the beam says, Greg, go up. So if I'm at negative 31.33 and I go up 55.33, that puts me at 24, and then I get brought down to 0. Okay? Oh my goodness. Okay, now we're going to determine some areas now under the curve in order to draw the moment diagram. So we're going to take it one shape at a time. Let's start with this triangle. Okay? We go. The height is 36 and the width is 6. So how do you determine the area of a triangle? Base times height over 2. So what's the area of this triangle right here? .108, and it's minus 108 because it's negative, right? Everybody remember that? Now, okay, let's take this rectangle right here. So we'll take each rectangle. So it's 28.67 times 4 and 8.67 times 4. So what's the area of this one and that one? 114.68. Everybody okay with that? All right. Now, this value right there is plus 8.67. Okay? Does anybody remember a real quick way of determining that distance? Well, we can do similar triangles. There's a whole lot easier way of doing that. What's the slope of that line? It's 4 because the load is 4. So if you take that distance right there, 8.67, and divide it by 4, what do you get? $2.17. Likewise, take 31.33, divide it by 4. What do you get? Say it again. 7.83. And what happens if you add up those two distances? What do you get? 10. I almost just wanted to, like, go like that a little bit. No, there'll be stuff to do. Trust me. All right. So let's take each triangle one at a time. So let's start off with that one, this one right here. What's the area of that triangle? 8.67 times 2.17 divided by 2. 9.41. That's positive. And what about this one? What's this one? 245.31. Everybody else getting this? Make sure everybody's following along. And then the last one, 24 times 6 over 2, so that's 24 times 3. That should be 72. Has everybody got that? Okay, now, let's check to make sure our values are correct. I want you to add up all the numbers that are positive. So that, plus that, plus that, plus that. All the positive numbers, and tell me what you get. Yes, sir. Say it again. 122 point what? 0.66? All right. So let's add up the positive numbers and tell me what you get. Anybody have a value? 230.77. So let's add up the negative numbers and what do you get? 230.660. So it's basically like 230.7. I mean, there's decimal rounding and whatnot. But basically, we have the same positive area and the same negative area, which means that the sum of moments is 0. That's what that means. So that, obviously, we got something that works. Now, so now it's time to draw the moment diagram. Okay, so we start at 0, and then let's see if y'all remember this, right? From here to here, we're going to go down to 108. All right, so let's do the values first. So from here to here, we're going to go down to 108, and then from here to here, if I'm at negative 108 and I go up 114.68, what does that put me at, like 6.68? Did I do that right? Right? Okay. And if I'm at 6.68 and I go up 34.68, what does that put me at? All right. Okay, from here to here, okay, so what do we got going on? So if I'm at 41.36 and I go up 9.41, what do I have? 50.77. I'm at 50.77. I go down minus 122.66. Basically, that should be about 72. Is that what we're getting? Like plus or minus some decimals? Yeah, so 72. And then that's going to bring me back up to 0. Okay? Is everybody okay with that? Now, let's pop quiz this, okay? From here to here, is this going to be a straight line or is it going to be curved? Okay? Now, here we go. Option 1, option 2. Little to a lot. Little to a lot. Option 1. Yes. Yes. We're just getting, yeah. You're exactly right. We can't answer the question. What is the answer? 108. Yeah, it's 108. So, and I'm actually going to get back to what he said a little bit ago because I want to get back to testing strategy because he had a really good point.
Can we stop once when we saw that 108 at the beginning?
You're-
All right, that's
You're right, but
max.
practice and let me also, hey, hold on. Let me say a couple things. You will very possibly get questions on the exam like, here's the shear diagram, what should the moment diagram look like? And you'll, instead of getting numbers for A, B, C, and D, you'll get like shapes, like this is a moment diagram, this is a moment diagram, and you have to pick one. So having an understanding of what this stuff looks like is actually kind of important for the exam. So I know kind of important, it is important. So everybody okay with this? All right. From here to here, what does it look like? Straight line, like constant shear, constant slope. So straight line. Another straight line here, right? Now, this is going to be tough to draw, so bear with me if it looks a little weird, but is this going to go like that or like that? Option 1 or option 2? 1. Yeah, so lot to a little. And then this one's going to go little to a lot, lot to a little. And so which one was 108? D. Okay. Is everybody okay with this? Now let me say a couple things, okay? From a test-taking strategy for this particular problem, once you had your points plotted out, you could have stopped and said it was 108 very easily, okay? Now, I want everybody to pay attention to this, okay? He brought up a very interesting point. What he did is he looked at the original structure, and he said, well, both of those cantilevers are 6 foot long. Like this is 6 foot long, and this is 6 foot long. And on the right, it's only seeing 4 kips per foot, but on the left, it's seeing 6 kips per foot. So what he said is, can we just ignore the right cantilever because we know whatever the maximum bending moment is, it's not going to be on the right. And he is exactly correct. You could have drawn your shear diagram and drawn your moment diagram to stop. There is one advantage to actually going through and drawing the shear diagram from start to finish, and that's this. When you add up all the positive areas and you add up all the negative areas, it should balance out. And if you stop drawing your shear diagram here, you won't have that area to balance with. See, if you have an arithmetic error, let's say right here, if you don't have that value, you won't be able to check it. Does that make sense? So that was a good point. And you know, if you're confident in your your math, then you don't have to worry about it. But if you need the extra check, that's a good place to go. So, is everybody okay with that? That was a really good point to make. Any questions before I go on? All right. Okay. bringing it back. Okay, so for the plane truss shown, what is most nearly the horizontal deflection at joint B? Okay, for all of these members, they have the same E and A value, which more often than not is pretty common on the exam. Usually with problems like this, they're not trying to confuse you by throwing a bunch of different E values and A values at you. It's more about determining whether or not you know how to do this. And so this is a problem where we utilize the principle of virtual work, the unit load method, right? Remember, we're determining the horizontal deflection at B. So we place a horizontal load at B in the direction that we assume, and so on and so forth. Everybody remember that? Now, there's a nice thing about this problem. How many loads are on the structure? And then the real structure, on the real structure. Yeah, how many loads are there? One, right? And what is that load? It's 60 kips, right? So let's just make up some numbers, okay? Let's say that once we do our analysis of the real structure, that member AC is seeing like 200 kips, okay? That's due to this load. How do I determine what it is due to a 1 kip load? All right. If this is 60 kips and that's 200, how do I determine what this is if this is 1 kip? Just divide by 60 is what I'm saying. This is sort of like the principle of influence lines, right? If I put a load right here in the middle of this table, right? If I can put 10 pounds on this table, that's 5 and that's 5, right? If I put 100, that's 50 and that's 50, right? It's all just half, right? So it's basically the same thing, right? What's that? I think I did, didn't I? Was that?
Yeah, because the whole semester we only did one direction. And on the test you did the other direction.
I mean, this is what happened. Hold on. What's that? I think I took up very little because you did know what you were doing, but
Just like thinking about what we were doing.
I didn't read directions. All right, hold on, everybody. All right, so in general, I know. In general, in order to determine the deflection on a truss at a particular point, we sum up the following quantity, right? We do little f, big F, L over EA. Y'all remember that? Yes, it is. That's a good question. The answer is yes, it is in the reference manual. In fact, this is pretty much the only thing in the reference manual in regards to deflection. So it's sort of the reference manual's way of saying this is what you need to do. So, and another thing to keep in mind when it comes to solving the deflection on trusses, remember there really is no other way of doing it other than an approach like this. All right. Now we have an E value of 29,000 KSI. We have an A value of 2 square inches. So right off the bat, we can go ahead and make our life easier and say that EA is 58,000, and that the units come out, that's kips. All right? The real structure. Okay. So here's our real structure. Now, unfortunately, when you're doing a principle of virtual work, you got to solve the whole truss. If you ever get a problem like this on the exam, the truss will be small, okay? Because it just is what it is. What I'm going to use is the method of joints to solve this this truss because it's so small and because I need everything anyways. All right. So here's the structure. All right. So we've got a 60 kip load right here. All right. This is B. This is C. All right. We have a hinge right here. We have a roller right here. This is D. This is A. All right. This is 20 feet. This is 20 feet. And this dimension is 10 feet. And so I know my structure is way out of scale, but what that means is that this member is 1 to 2. This member is 1 to 1. This member is 1 to 2. Like I said, I know my scale is way off. All right? So here's what we've got going on. We've got a hinge here at A. Well, I can tell you right now, I know what that reaction is. What is it? 60. All right? All right? What I'm going to do is I'm going to sum moments at A to determine the reaction at D. So let's sum moments at A. All right? Now I propose I've got 60 kips acting at a moment arm of, this was, or I think this whole distance from here to here, that's 20 feet. I know my scale is horrible. I'm not. I don't care that much, but I am going to move that up. 1, 2. So, all right, so we have 60 kips times 20 feet. And so that has to be counteracted by dy at 40 feet. Is everybody okay with that? Did I do something wrong? Everybody's like, so that means dy is going up right here. So this is dy. And so I have dy times 40 feet. So can anybody just take a look at this and tell me what dy is going to be? 30, right? 60 times 20 has got to equal 30 times 40. So dy is 30 kips going up. Everybody okay? Is that okay? I just shortcutted that? All right. Well, I'm making sure everybody's following along. And if I sum forces in the y direction, if dy is 30 kips going up, what is ay? 30 kips going down. So ay goes down. Yeah, now we're going to do the truss analysis now, like the method. Is there any load at C? Yeah, there's like, I mean, if I solve if I do method of joints at C, there's going to be like force in that member, force in that member, and force in that member. I'm doing, give me a second. I'll get there, I promise. What's that? Yeah, that is true. That is true. All right. See, I'm in the mindset like I literally just did this today, so. But I know for a lot of you it's been a while. So. Okay. Has everybody got this? All right. Okay. We have to solve. All right. This is where I want everybody to pay attention. We have to solve the entire structure. Okay. Can we start at A? Can we do a method of joints analysis at A? We could, but there's a problem. Anybody remember what the problem is? We have two diagonals going in at A, so it's going to make our math a little more difficult. And we can't start at B or C. Why can't we start at B or C? There's too many unknowns. Remember, whenever you do a method of joints analysis, you can only do a method of joints analysis where there's no more than two unknowns. So we can't start at B and we can't start at C. We could start at A, but there's two diagonals at A, and that makes our X and Y equilibrium a little tough. So I'm going to start my method of joints analysis at D. Okay? What's that? All right. So here's this. This is 1 to 2. All right. And you're going to notice how I do my method of joints analysis pretty quickly, okay, because these slope ratios are pretty simple. All right. Now, are there any loads on joint D? And it's 30 kips going up, right? Now, watch this. If I have 30 kips going up, I got to have 30 kips going down, right? Now, if this is 30 kips going down, what's the magnitude of this horizontal? Like if this is 30, what's that? 60. Is it going to the left or to the right? To the right, because it's in compression. So this is 60, and that is 60. So I'm doing my method of joints analysis real quick because this is pretty simple, okay? And you all have seen this stuff before. So it's not like when I was teaching you instructional analysis where it's like, okay, let's document every single force. You all been through this before, so I'm going through it a little faster. Everybody okay with this? All right. So what do we know from this analysis? We know that CD is 60 kips in tension, and BD is the square root of 30 kips squared plus 60 kips squared, which is what? Now that I need some help on. Say it again. 67.08, and that is what? Compression. Everybody remember that? All right, any questions? Okay, now, since my drawing of my truss is just absolutely horrible, let me go back to this. Okay, so I've solved for these two members right here. Okay, so you tell me what to do. Should I do an analysis of joint A? No, I still have two diagonals. Now I have joint B or joint C. I'm going to do joint C because it's one less load to deal with, although it doesn't really matter. I'm lazy. So now we're going to look at joint C. All right, so here's the joint. We have a member going up, a member going this way, and then we have a diagonal that's at 1 to 2. Now, do we know any of these forces? This is 60 kips, and it's in tension, right? So remember, tug of war, right? If you have a rope and I have a rope and we're yanking on it, we're doing the same thing, but we're acting in opposite directions, okay? And so this is pretty straightforward. If this is 60, actually, let me draw that. Let me put this in red because that I knew. I knew this one. This is 60. If that's 60, that makes this one 60. And if that's 60, what's the vertical? 30. And is it 30 going up or going down? Down. And so that makes this 30 going up, right? Pretty simple, right? So that means that BC is 30 kips in tension, and that means that member AC is square root of 30 kips squared plus 60 kips squared, which that one I can do because that's 67.08 kips in tension. Is everybody okay with that? All right. I don't want to put this on another screen. I'm just going to put that right there. All right. You tell me, do you want me to do joint B or joint A? It doesn't really matter at this point. You conceded, so we're going to do joint A. All right? All right? So here's our joint, right? We know this is 60 kips. We know this is 30 kips. This is 1 to 2. Or, sorry, I got that backwards. This is 1 to 1. Now, do we know any of these forces? The 60-30 on the bottom member, right? So that is 60 and that is 30. So what's going on vertically and horizontally on this member? Big old goose egg, 0 and 0. So AB is a zero force member. There is, and this isn't the best structure to identify that because it's not as readily apparent. Okay, I can show you that after this. Let me finish this one. Okay. All right. Has everybody got this? All right. So far, so good. Okay. If you've got this, I want to go back to the image because I want to illustrate the strategy. Okay? What we're trying to do, let's keep the eye on the prize. We're trying to determine what is most nearly the horizontal deflection at joint B. Okay? So remind me how this works. Okay? We do the real analysis, right? We analyze the structure when it's subjected to the loads that are on it right now. That's what we just did. Now, the virtual analysis. How does that work? Well, we remove all the loads off the structure, right? And we take a single unit load, a single 1 kip load, and we place it at joint B, right? And we place it in the direction that we assume it's going to deflect. So which way do you think joint B is going to deflect? To the left or to the right? To the right. So here's the real analysis. And the virtual analysis is just replacing that with 1 kip, right? So couldn't we take all those numbers we just derived and divide them by 60? Why redo the analysis? We just did it. Oh my goodness, this isn't that bad. Oh. Oh, okay. All right. Now, has everybody got this? Okay, all right. Next sheet. If you've got that, then your virtual work analysis is real simple. Okay? All right? All right. We have 5 members on the structure. We have member AB, member AC, member BC, member BD, and we have CD. All right. Now, help me out. What were the results that we just got? Like this one was 0. What was AC? in tension. So we treat that as positive, 67.08. What about BC? And that's tension. Okay, BD. And then CD. All right? And so that's our real structure. Okay? For our virtual structure, normally we would need to do the structure or analyze the structure again, but because we have a very special case in this problem, I'm just going to divide all these values by 60. So that one's 0. Bless you. Because it's easier to pull the image up. Because for our real analysis and our virtual analysis, we just happen to be looking at the same point where the load is. You would. What I'm saying is, what if the real structure had load there, and load there, and load there? Because our real structure just happens to have only one load on it right here in the direction that we're interested in, we don't have to do it again. That's what I'm saying. That's a good question. Everybody else okay with that? If any of the loads were different, we'd have to redo all this. So. No. No. And if they did, it would be like a 3-bar truss. Like it'd be really small. So like where you'd have to do like maybe one or two joint analysis and you're done. So. All right. So going back to this, we need to divide these by 60. So what's this first one divided by 60? Okay, and so that's going to make this one minus 1.118. And dividing this by 60, that's a half, and that's 1, right? The only other thing that we need is the member length, right? But if you recall, when we do virtual work, we need the member length in inches, okay? So let's do a simple one, okay? Member BC, how long is member BC on this structure? 10 feet or 120 inches. Do we need to worry about member AB at all? It doesn't matter because we're going to multiply everything and get 0, okay? So member, let's see, CD, how long is member CD? 20 or 240 inches. The only thing we need are the other two. So what's the length of member AC? Like remember, I know member AC and BD are the same, so. In inches. Like that? All right, and so that's the case here. All right. Once you've got those, remember it's FFL over EA. So we'll do little f, big F times L, and all that's going to be in inch kips. So I'll start you off. The first one's 0. And I'll tell you what, if you give me the next one, I'll do the rest. So what's for row AC, what's AC going to be? .6 or what? 20,120. 3.5 like that? Okay. All right. So that's true for member BC, 1,800. Member CD is 14,400. And this one's 20,123.5. So when you sum those up, I do need some help there because my rounding's a little different than yours. I got 124.6, but I was tracking decimals and whatnot. All right? So remember, oh, I was about to say, don't tell me my pen's dying on me. So therefore, our deflection is summing up the little f, big FL over EA, which is 56,447 inch kips divided by 58,000 kips. Remember, we did our EA at the very beginning of the problem. And so what does that come out to be? And so that is what do you think? Can't use RISA on the FE. All right. In the interest of time, this is what I'm going to do. Let's look at our remaining examples. I knew we were going to be short on time at the end. Okay? Example number 4, this is what I'm going to do. I'm going to go ahead and tell you that the answer to example number 4 is D. Okay? Now, or wait, hold. Yes, it's D. Sorry. No, it's D. All right. Here's what I'm going to tell you, and I can post a video on this particular example here in a little bit, but there's really 2 things that you need to keep in mind. You could use the unit load approach, but I would highly recommend against it. Instead, what I would do is go to the beam aids that were referenced earlier. If you go to the manual, there are beam design aids in the manual referenced for determining beam deflections for these cases. The only thing I would say is just make sure you convert everything to consistent units, and I'll post a video on that later. But they're basically plug and chug. What I would like to do is spend the remaining amount of time on this one. Okay, so is everybody okay if I just skip 4 in the interest of time? Okay, all right. So let's go through example 5. This will be our last example, so we're certainly not going to have time to do influence lines today. So a floor system for use in an office building utilizes 45-foot long floor beams spaced at 9 feet. So remember, the length of the beam is 45 feet, and the girder spacing is 9 feet. Okay? The floor is to be subjected to a service dead load of 50 pounds per square foot and an unreduced service live load of 80 PSF. So y'all remember that? We've got to break out the live load reduction. All right? Using LRFD load combinations, what is most nearly the maximum factored bending moment on a given floor beam? So because we're dealing with simply supported beams and uniformly distributed loads, we can use a maximum moment of WL squared over 8, right? So I think that's pretty straightforward, okay? Let's chug this one out. I think you're going to find this is pretty simple. All right. So we know that the span length is 45 feet and the girder spacing is 9 feet. Okay? So let's take care of dead load first. That's a great question. Okay? Now I have here, the page number is probably different, but it's in the structural design section under civil engineering. So if you go to the table of contents, there's a section for civil engineering, there's a section for structural analysis. This should probably be right before concrete design. And does anybody have a page? It's probably like 140, 150, something like that. 159. They should have your load combos there as well as live load reduction. The live load reduction formula should be in the manual. All right. Now let's take a look at the dead load, okay? The dead load, we have a pressure load of 50 pounds per square foot, okay? If you remember, I know everybody's packing up, but we got time on this one, all right? If you have a pressure load, remember what you can do is turn that into a distributed load by applying that pressure load over the tributary width, right? Does anybody remember what the tributary width for floor beams that are 45 foot long, spaced 9 foot are? It's 9 feet. It's the girder spacing, right? Remember, the girder spacing is the same thing as the tributary width. So this is 50 pounds per square foot times 9 feet. So that's 450 pounds per foot, right? Remember that? So if I have a distributed dead load, I can then compute the distributed dead load moment by taking the dead load and multiplying it by L squared over 8. So that's 450 pounds per foot times 45 feet squared divided by 8. I'm going to need some help on that.
113,006.
Say it again.
113,906.25.
0.25. Okay, and what are the units? No. Foot, not pounds per foot, pounds times feet, or foot pounds. Foot, yeah, because because it's the feet squared. Lubs. All right. Now, this is exactly the exact same thing that we have to do for live loads, but there's one additional step, right? We have to reduce, right? Okay? So, okay, in order to perform live load reduction, we need a couple of things. So first off, we know that we have an unreduced live load of 80 pounds per square foot, okay? So we need a couple of things. The first thing that we need is the tributary area. Now, what is the tributary area of this beam going to be? Like, how do we compute it? It's the length 45 times the width that it's responsible for, 9 feet. So that's the tributary width times the length. So that's 45 feet times 9 feet. And what's 45 times 9? 405 square feet. Now, we need one more thing, and that's the live load element factor. Anybody remember what the live load element factor for beams? What's the live load element factor for beams? It's in the manual. 2. Remember, if it's 2 for beams, how about this? What is it for columns? 4. All right, so KLL is 2. So then what we can do is we can perform live load reduction to determine a reduced live load. So that's 80 PSF times 0.25 plus 15 over the square root of KLL. Oop, that's a subscript. KLLAT. So that's 80 PSF times 0.25 plus 15 divided by the square root of 910 square feet. Did I do that right? 2 times 405, 810. And so what's my reduced pressure load going to be? 62.16 PSF. Remember, there's a limit. You can't reduce it more than to more than 40%. 40% of 80 PSF is 32, so that's fine. Like if we computed this and it ended up being like 3 PSF, remember you can only reduce it so far. All right. And so now that we've got this, we do the exact same thing we just did. We determine our distributed load, 62.16 PSF over the tributary width of 9 feet, which is what? we determine a live load moment. And that comes out to be
141,616.
and that's foot-pounds. And now we can factor. And what's our load combo? This you should remember. How many times we use it in concrete design. There we go. 1.2 times the dead plus 1.6 times the live. So factored loads. So our dead load moment is 113,906.25 foot-pounds, which what I'm going to do is I'm going to say 113.9 foot kips. And then our live load moment is likewise 141.6 foot kips. Therefore, our factored moment is 1.2 M dead plus 1.6 M live. Has anybody got a value on that for me? So 1.2 times 113.9 and 1.6 times 141.6. 384.84. Do I have a second on all that? I was to say, that's not what I got 363 something. Like 363.3. So it's 113.9 and 141.6? Was it 119.3 or something? That'll do it. All right, and so which answer is that? B. Now, one thing I want to mention, this is a little different than we used to do it in concrete design, because what we used to do in concrete design is we would take the dead load, like the distributed dead load and the distributed live load, and then factor that and just do WL squared over 8 once, okay? The only thing to keep in mind, and this is what like students would always, we get some mess ups on like homeworks is, well, what happens if you have a distributed dead load but a point load for live load? And I would say, well, what people would do is say, well, I'll take that point load and I'll just turn it into a distributed load to make my life easier. And then what would I do? Don't do that. So I want you to get into the habit of computing the dead load moment separately, the live load moment separately, and then get 1.2 M dead plus 1.6 M live. Everybody got that? Hold on. I know y'all are packing up, but I got a question and then some housekeeping. Yes? That's a great question. All right, hold on. All right, everybody, y'all need to listen. Shh. Ask that again.
There's 2 equations in the manual for one with live load reduction, 1 floor, and the other with 2 or more. How do you know which one?
It's a great question. The answer is, so the question was, when you have live load reduction, when do you account for single floors versus multiple floors? And the simple answer is this. Beams only support single floors. Columns tend to support multiple floors. So that's a simple answer for the exam. It's not always the case, but for the exam's purposes, that's pretty simple.
I think we use the multiple floor.
We what?
Multiple floor equation has KLL and AT and 40%, but this single has 50% and KU.
That's a typo. No, that's a typo. Hold on. Just if you all hold on. If you all are on the manual, the difference between the single floor situation and the multi-floor situation is the limit on the end for nominal for your nominal resistance. For single floors, you can't reduce more than 50%, and for multiple floors, you can't reduce more than 40%. That KU versus KLL, that's a typo. I'm telling you, that's a typo. Because you tell me, are there KUs? Yeah, that's a typo.
So we can't reduce that more than 50%.
Yeah, but we didn't because we weren't anywhere near that. One other thing. All right, I know we got 2 minutes. I'm not posting a quiz this week. I'm posting a quiz next week where I'm combining this and concrete design into one big topic. So I will talk about steel, but I'm not going to put it on the quiz because, yeah, you all will learn all about it next semester if you decide to take that horrible professor teaching steel design next semester. And for those of you on the recording, that's me, so I'm making fun of me. All right. I'll see you all whenever I see you.